Hello, my name is Sergey Bratus. I'm a program manager at DARPA Information Innovation Office, and I'm here to talk to you about the program that ITO has been running in secure parsing, which we call safe documents. Next slide, please. Or SafeDocs for short. It's great to be here, and it's a privilege to speak to the group that is doing brilliant projects such as EverParse. You will see that our efforts are, in a sense, complementary and, in a sense, address different set of challenges. But there is a deep connection on the fundamental research side between these challenges. And I hope that you will engage, you will reach out to our fundamental research performers, and there might be a collaboration coming out of this. SafeDocs or Safe Documents is a 4-year program, and it's now in its 3rd year. And it has produced a number of results that I will show you. You see the graphic here. Next slide, please. And SafeDocs starts with the observation that we've had the problem of secure parsing of actual information interchange formats and document formats since pretty much forever. Why is it not solved? We have great advances in verified programming, where we can start with a specification and create programs that can be proven functionally correct and true to the specification. But the moment you touch real-world programs and real-world formats, the situation blurs considerably. First and foremost, you will not find a machine-readable specification. Your specification will be written in English, and even though this is in English of technical standards, it is still not unambiguous. As an example, and this is our test case in the Safe Documents project, let's take PDF. PDF has over 900 pages of core format documentation, many more of various related standards, and we've been able to identify and report as candidate edits over 60 ambiguities, which are being corrected in the ISO PDF 2.0 standard. So it starts with establishing a machine-readable view of the protocol and this of the format, and this can only be done by observing what we see in the wild. Then we can actually hope to verify parsers with respect to how they verify, validate the data that they receive. Now, you might say that this is a problem that has been a mainstay of computer science, and this would be true. We have the Chomsky hierarchy of grammars, we have context-free grammars, that we have all kinds of tools to auto-generate the code to parse, and we have the more recent advancement in parser combinators that make it easier for programmers to create declarative definitions of programs. However, context-free grammars don't quite do it for modern complex data formats. And neither do parser combinators, but with a different caveat. Context-free grammars do not concern themselves with the objects and relationships encoded in electronic data formats and extracted from those data formats and then passed to the rest of the code, so that the rest of the code has to rely on how these objects and relationships have been validated and whether they have been all validated. A parser combinator can do that, but you have to provide the code for verification in a semantic action. And so you leave the domain-specific languages for specifying grammars, and you are, again, as a programmer, in a domain of unsafe code where you might accidentally corrupt memory and make your parser as vulnerable as an ad hoc, hand-rolled parser. So we need a way of finding the objects and relationships and specifying them declaratively and creating the code that validates all of those and can be relied on as the front end, after which all the rest of the verification can take place. Next slide, please. And in this, we encounter the messy real world in which we have to comprehend what is actually out there. Because even when a format is standardized, as PDF has been since the ISO took over from Adobe in the maintenance of its specification, we still can be sure that what you find on the internet or in your own stash of files is compliant with the standard. In fact, you are pretty sure of the opposite. Over the years, repairing files or repairing small benign or presumed benign malformations in files has been the mainstay of all implementations. And they disagree about what they consider benign malformations and how they fix it. And so there are dialects that diverge from the standard and between each other. This is a considerable problem. You need to actually observe the data in the wild to derive a machine-readable, rigorous, unambiguous definition of the de facto format as it exists, not only as it is transcribed. Then you have to establish new type theories for actually describing those objects and relationships. And context-free grammars or context-sensitive grammars or dependent types only get you so far, because the development of modern data formats has not heeded theory as much and has created its own favorite constructs. Finally, we have to make sure that these descriptions remain machine-readable and that we can generate code from them that could be verified. Occasionally, we might find that the format as it is specified cannot be made precise, cannot be made unambiguous, and we end up with creating what we call a safe subset, a stricter subset of a data format, which has code that can be verified. Next slide, please. And then, of course, there is the moment of code production itself. And we want that code to be verified in the best proof assistance and logics that we have, where we encounter the challenge of what is the right functional correctness theory for a parser. And surprisingly, there isn't a clear answer to this in the literature, not in general. We need new type theories and logics to answer this question. And then performance is a concern, because the code verified correct may not be the most performant. In fact, this is the most common excuse in rolling ad hoc parsers. Well, we have to make verifiable implementations also performant. And since we actually want regular programmers to write and generate that code and handle the specifications, they have to be accessible. We have to hide the math and make it so that you do not need a math PhD to parse a format. And these are the fundamental challenges of the Safe Documents program, and I hope to tell you how we are handling them. Next slide, please. So SafeDocs has addressed a number of formats, most notably PDF, but we have been looking at the ICC color profiles, which are an important part of modern operating systems, often in the kernel of the modern operating system, but also when they are not in the kernel, they could still take down a platform, as we have seen with an incorrect implementation of ICC profile handling in Android recently, where a background would essentially soft brick the phone. We have looked at image formats and at the network formats, which is, of course, closer to EverParse. We have been able to point out a lot of ambiguities and help eliminate them from the ISO standard. And we are redefining how data sharing formats, information interchange formats of the future could be designed so that they are unambiguous by construction. We hope that in years from now, this will be the way to define formats to avoid ambiguity, because ambiguity is insecurity. And so far, our parsers have been proven correct, and those that they have not been proven correct yet have stood up to hundreds or thousands of hours of fuzzing and billions of document samples. So I think we are doing well and getting there. Next slide, please. And of course, you will notice that there is a considerable intersection between the fundamental research challenges with EverParse, which aims to produce functionally correct implementations of parsers. We have a broader set of topics and a richer set of languages and dependencies to validate and to capture. But of course, performance is also important to us. It's just that this is not the single concern besides correctness. Expressiveness and being able to capture real-world formats is important. Next slide, please. And so the program has a number of directions. If you attended this year's or previous years' Language Theoretic Security Workshop at the IEEE Security and Privacy Conference, Oakland, you saw a few of those results presented. Today, I want to tell you about some of the highlights. There are many more. And these are our data definition languages, which aim to describe objects and relationships in actual real-world, modern, divergent information interchange formats. And these are Daedalus, the play on DDL, of course, from the Galois epiformer on SafeDocs, parsley, another DDL from SRI based on SRI's PVS system, and another development which is a parser combinator in C, which is called Hammer and is developed by a performer called Special Circumstances, the original authors of Hammer, in conjunction with the team from BAE, where they help validate and verify parts of it. I won't be saying much more about Hammer today because we don't have the time for it, but I direct you to the GitHub of Hammer and parser combinators in C. What? Don't look at me like that. Really, you can do this. And you can keep the subset of C in semantic actions to be very expressive and very succinct, being able to produce very small, very short, runnable C declarative definitions of files. Last but not least, we have the first ever machine-readable model of all objects in the PDF standard across all versions. And it is called the Arlington PDF model. PDF standards are named after places, and this machine-readable model or document object model for PDF is called Arlington. This has been provided by the PDF Association, and it has been published as of May this year. You can find it on their webpage and also on GitHub. Next slide, please. I would like to start with Daedalus, which is a data definition language that is expressive enough to capture objects and relationships in formats such as PDF. This is a tall order because it takes care of data dependencies, which are many, referential integrity constraints, which are many, and situations where you have to switch to a different place in the format to parse from there and then come back, which is provided by a new abstraction, Firstclass input streams. And this code is available on GitHub for your perusal. It takes quite a lot from the dependent type theory, as you can imagine, but it translates to C++ or Haskell. The C++ features an ownership-based model. Those of you who are looking at Rust might like that. And there is a server, a language server, which we could use from VS Code or Emacs when writing Daedalus descriptions of your format. Next slide, please. So I will not dwell on the syntax. You will find papers published about that at the LangSec Language Theoretic Security Workshop. But of course, you would expect the combinator language flavor from that. It focuses on data dependencies and on unambiguous definitions, including removing ambiguity from alternatives, the way parser expression grammars do, with a biased choice. And that turns out to be a really significant way of reducing the workload of verifying resulting parsers. We have tested it on PDF, but also on other formats. For PDF, it's good enough for text extraction and extracting which actual objects and relationships are found in the file, which streams are found in the file. Next slide, please. But we've applied it to other formats such as color profiles, ICC color profiles. In fact, using our tools and using our definitions, we have been able to identify and recommend some of the ambiguity fixes to the format, but we also were able to find that the recent issue with parsing ICC profiles, with handling ICC profiles, was actually not the format's fault, and not the fault of the format design at all, but rather of the implementation that took to processing it. I would like to point out that first-class streams are extremely important for being able to capture the essence of the format in just under 600 lines of code in Daedalus. And this is a sizable and important format. Again, you will find it in operating system kernels pretty much everywhere, as well as in really expensive imaging equipment, such as medical imaging equipment. It incorporates an arithmetic which we can also model using the expressive power of Daedalus. So we go much further than syntactic validation, which will hopefully help avoid any issues with parsers generated from our descriptions in the future. This is an ongoing work, and we hope to continue it. Next slide, please. We have another competing DDL based on a different flavor of formal verification, with Daedalus being largely based on the calculus of constructions, think cock. Parsley uses PVS as its formal workhorse. PVS, of course, has been around for a long time and has acquitted itself really well in code verification. Parsley defines attribute grammars and was the first, to our knowledge, implementation of parsing expression grammars, PEGs, to be formally verified and proven correct. This result has been published last year. For performance, Parsley defines the semantics, the operational semantics of an abstract machine to which the parser is compiled and executed. And it's capable of producing certified parse trees, that is to say, proofs of parses, proofs that parses are correct in the spirit of translational verification. Next slide, please. Here on this slide, you see some of the syntactic details of Parsley. And, of course, it's strongly typed with dependent types. And it also has a slightly different concept of streams and stream support, which it calls views and buffers. So, again, we have abstractions for nested format types and for referential integrity between several points of parsing, which is very common in document formats. This is key to securing formats like PDF or JPEG or image formats, or self-describing formats like the data distribution service. Next slide, please. I can't talk a lot about the Parsley abstract machine, but as you can imagine, memoization is critical to parsing expression grammars. And this and other important operational semantic aspects are captured in the formally defined operational semantics of this machine. And from this machine, you can further just-in-time compile it or optimize it. But this is an approach that heeds the algebraic types approach to creating parsers, staged parsing, and creates performant parsers that are also expressive and could be proven correct or could provide translational correctness proofs with proof of parse. Next slide, please. But of course, you need to use the A data definition language to encode something. And that something is a document model. So for the first time ever, so far as I know, we have produced a machine-readable model of the PDF format. The PDF Association, a performer on the SafeDocs, has produced and published it this year. It covers every version of PDF spec and does so in a no-code way, creating a schema for TSV utilities, but of course it can be translated to DDLs. And it helped find a lot of issues with existing commercial and open source validators of PDF files, because once you start capturing the essence of the format in a formal way, inevitably you encounter surprises that even the experts that have been in the field since its inception might be surprised by. This model has been published, and I believe that this is a very important advance in defining what the format is and how it should be handled from now on. Of course, we also need to capture not just the standard, but the actual dialects of the format based on various generators. that have been used over the years. But now we have a baseline of machine-readable, human-intelligible definition to benchmark or baseline those dialects against. And this records the ISO standard for PDF 2.0 and the previous standards. Next slide, please. And just to give you an idea of what the standard looks now, you are seeing a marked up excerpt from the standard, from the actual ISO document, and the tables would be familiar to you if you've spent time with those. The Arlington PDF model interprets and, as necessarily, corrects, when ambiguous, those kinds of definitions. Next slide, please. And it turns out that there are quite a few ambiguous parts in the standards language. For example, the ambiguity as to how far the indirection may go and how far your validator may need to follow a chain of references between PDF objects to extract what is ultimately might be just an integer, a length of a stream. Next slide, please. But it may be more important than this. Your objects in PDF are, of course, dictionaries. The type of the object is determined by a key, but that key might not be there. So your renderer might have to take a guess. And different renderers might take a guess differently, depending on how they interpret a particular deviation or a malformation that they consider benign. So creating streams and documents that are interpreted differently and therefore rendered differently, the parser differentials, is very much a security problem. And we are addressing the ambiguities that are at the root of those, rooting them out one by one. Next slide, please. We hope that our Arlington PDF model will help EverParse efforts and will help any other efforts that are concerned with parsing or validation or comparison of files or repair of files. Because, again, for the first time ever, we have a formal model, an unambiguous machine-readable model of what the objects and relationships are. So I encourage you to look it up and connect with us and with the PDF Association. Next slide, please. And last but not least, I want to mention two tools. You will see a link to the blog post describing them, that help you find files that are polyglots, that is to say, can be understood as a valid PDF and a valid zip, and a valid bootable volume, and a valid TrueCrypt module, disk image, and a valid SNS game image, and a valid JPEG, and many more. You can read about those in that blog post. So understanding the polyglot properties designed into formats, often unwittingly, is what polyfile helps you do from the Trail of Bits working with Galois. And there is also the polytracker tool that helps you instrument a parser that you have in C and C++, with a form of very efficient taint tracking, so that you can see for every byte in the file what code handles it and what syntactic or semantic construct in the file format is being interpreted at each point. So this has been a great tool for exploring existing parsers, and we encourage you to try it out. Next slide, please. And with that, I am out of time. This is a large program that has produced a number of other practical and theoretical results. Unfortunately, I can only select a few highlights, which I thought would be interesting to you in connection with EverParse and your other system design efforts. I would like to close by saying that this approach to information interchange formats is something that I personally believe must become the very first step of systems engineering. And before you write any code, when your system is still a collection of boxes and arrows, what travels on those arrows has to be defined unambiguously, machine-readably, human-intelligibly in a data definition language. And if you have a legacy system, then you have to extract and backport that definition, again using a DDL and the file and format exploration tools. We have an internet observatory for PDF in which we have processed upwards of 20 million files. I think our goal is 300 million. And our discovery has so far been quite successful. Thank you.